Let's derive the electrical potential due to a uniform charge thin spherical shell. So you have a sphere whose thickness is uniform. So it's a shell. So basically things are empty in the middle. So we can have them to be, say, positive charge throughout. So it's uniformly distributed. Now, so the derivation will start like this. Consider a uniform charged spherical shell of radius r. So let's call this as radius r. Carrying a charge of q. Okay. Let's consider a point P, say over here, at the distance of r from the center. Now, we have three possibilities. One, outside the sphere, on the sphere, and inside the sphere. Let's have a look how things vary, how the potential varies in these three places. So first place is outside. So if you guys remember the electrical field and all of that derivation, we know that a sphere acts like a dot or point charge, and everything else, the formulas and everything, behavior, everything else remains the same. That's what we have written over here. A spherical shell behaves like a point charge, keyword, can't miss that, when viewed from outside. Thus, the electrical potential will be given by what? K Q by R. So for R greater than capital R. Now, on the sphere. So here too it will be K Q by capital R. Then inside the sphere, this is where the things get a bit tricky. So let's have a look at this. This is a simple gravitational potential difference video, right? So I'm leaving an object at a particular height. Because it has access to a lower potential, it starts moving. Agree? So it starts moving because it has access to lower potential. What if the neighboring potentials were the same? Like in this case, 0. So say this is at 0 potential. So what happens? It won't move because neighboring are also 0. So it won't move. What if we have this scenario? What about now? Will it move? If I keep it in the middle, so clearly this is at higher potential compared to the first scenario or the second scenario or the previous scenario. Right? Let me put it in this way. Compared to previous scenario, it's the same, same slope, zero slope basically, but elevated. In this case, if I keep a charge, what happens? Right? It does not move. So this is how we can think of this particular scenario what we have over here. We have charges over here. They are at particular potential. They have a particular electrical potential. Now, will the charge inside or the space inside, will they be of different potential or the same potential? So that the charges per se, or theoretically if there is any charge inside, per se will not move. What should be the case? Right? Like this, wherein everything is the same potential and thus we see no movement. Since we are all talking about static scenarios, yes, there is no electrical field inside. We are seeing this from your Gaussian law because there is no charge. Again, coming from previous topic, not going to explain much. For this to happen, the potential has to be 0 from one end of the surface to the other and in between. The potential difference, not the potential. Potential difference has to be 0. And so V inside has to be same as on. It has to be this. Because if the difference has to be 0, then the inside too has to be same as the outside. Agree? So let me just put it this way. V inside minus potential on has to be equal to 0. That's what the difference tells. I mean, potential difference has to be 0. That's what potential difference is, delta V. But this is 0. As delta V is 0, V inside has to be equal to V on, is nothing but K Q by R. And finally, let's have a look at the graph. So this is the sphere. Again, this is not part of the graph per se, just to show that this is of radius R. So this is the distance, and this is distance, and that's your electrical potential. So potential versus distance graph. So we are looking at, right? So all of this distance is your R. Now, if this is your KQ by capital R, right? Say this height over here, then all of this has to be at same potential. So all of this space has to be at KQ by capital R. And post that, what will happen? It will reduce at the rate of 1 by R, something like this. So here it is 1 by R. Does it make sense? So that's about potential versus distance graph. Now pause, have a look.